This 6-bolt 4G63 block just got its final cleaning, paint, core plugs, and inventory complete. With that out of the way, now it's time to start its assembly. On the workbench behind it are pistons, rods, and a crankshaft that we're all going to get to know. And that's a little weird because rarely do parts get to make a whole bunch of friends first before disappearing inside the block forever. We'll always know they're the ones that are in there doing all the cool things that they do, but let's get this crank out of here, shall we? I'm sure that it sat in a tank of something at some point because it's a little bit cleaner than it left, but the warning message was written on there for a good reason. The crank is filthy, no matter what your eyes are telling you, and I'm going to prove that to all of you. Don't worry about the dust that you're going to see in the oil. That's nothing. That's going to come right off. The finishes all came out great for a crank with 148,000 miles. I got some grinding, some finishing, and some balancing done to it. You'll easily recognize the balancing work that was done because it doesn't match the factory balancing holes. And when you see this on a 4G63 crankshaft, be really happy because Mitsubishi had great quality control to begin with during these years of production, at least in comparison with what others were doing at the time. So seeing these additional balancing marks on a stout factory 6-bolt crank is pretty minty to me. Final cleaning of a crank means that you have to clean the inside of it too. And now I'm going to use those hose-wrapped wires that I used on the cylinder head to make a rig for this thing capable of hanging it at the right height inside of my ultrasonic cleaner. And this is a little bit controversial, really. There's lots of people out there claiming that you shouldn't do this to your crankshaft because it's going to shed foreign material into your bearings. I'll tell you right now, they're wrong. This isn't why. It's not because they knocked it loose that it contaminated their bearings. It's because they didn't do anything else to clean it out short of that ultrasonic cleaner, and they fell victim to the looks can be deceiving cliche. An ultrasonic cleaner isn't going to clean crank oil galleys out by itself, and I'm not aware of a push-button machine that can do that to a crankshaft. I'm just using this easily delivered ultrasonic cleaner fluid whose label I read less than 1/8 of, and whose odor is almost exactly like another ultrasonic cleaner fluid that I can't even get anymore. So my trapeze thing worked to keep it off the piezos that are all over the bottom of the tank. Those are going to eat up your parts if you set them directly on it, so that's why I did all that trapeze stuff. I turned it up to 68°C, which is about 150 degrees, because I want it hot enough to soften up the sludge that might be in there, and I gave it 15 minutes to work. The ultrasonic cleaner is obnoxiously loud with the lid off. Wear earplugs working around these things or get out. But understand that if you want to have a private conversation around electronic devices, this is precisely where you do that. Crankshaft lithotripsy. Let the sound waves clean your crank and destroy your microphones. Let's fast forward this, shall we? Thank you. There's practically nothing in the bath when I pulled the crank out of it. It just looks foggier. That's not any kind of confirmation that it's clean, but as I hurriedly start to try to oil and dry it, it's almost like I forgot this isn't an engine block boiling in a plain old thing of distilled water.
Should be rinsing it first.
Either way, I'm going to clean any remaining residue off, but I want to change its pH back to something normal first, so I rinse it. Tap water doesn't really matter much here. The part's hot and I'm about to oil it dry with a vigorous microfiber drubbing, and then drag it into the clean room for further inspection and to really get down to business, showing you that this crankshaft is filthy. And I know it sounds crazy looking at this. The crank has 4 oil galleys drilled into it that intersect 16 journal passages, and right after the factory drills those holes, they plugged it with a steel ball with an immense amount of force. It's the most interfering interference fit that ever interfered. Think about it. The crank has to hold on to that thing at 7,000 RPMs with 100 PSI of oil pressure behind it. You're not going to extract it. You have to drill that out. Or you get the most powerful solvent you can in a spray can, grab the straw, and bend it at the tip so that you can snag the dead spot in the crankshaft journal on your way by through that oil hole and shove it deep into the dead spot to blast and wash all that funk out. And here we are just on the first one. While you watch me do this, you'll see that the fluid comes out black, and much of this is so fine that it actually goes right through the coffee filter into the tabletop. You see those gritty chunks in the middle? They may be insoluble, but those chunks can certainly do damage to your bearings and journals, and we're just getting started. I treat this pretty much exactly the same way as I did the block. I keep repeating this until it's verifiably clean over something white. it helps you see it better because a whole lot of what comes out tends to be the fines, and you need to see those leaving. Sorry, no gold anywhere. I was hopeful. It's all just that worthless black sand stuff that hangs out with it. But anyway, if you clean your crankshaft like this, don't do it over just one side and quit, because it's the turbulence and flow of the pressurized solvent escaping that's really going to do most of your heavy lifting. Do it again from the other side too, and repeat until it comes out clean, because the way the straw bends, you'll be able to create the same flow pattern as you did from the other side, and kind of do the opposite thing. And the plug's a ball, so you can use the straw to feel around inside of there and make sure that you feel it going all the way down to that plug. See, there's a nasty chunk blasted out right there. It was holding on really good. Kind of hard to see because it's dark gray, but that's the big one. And when I touched it, it went squish. It appears to be Molly Lube, but it's sticky though. It probably is Molly Lube, but it's got that black carbon sand stuff mashed all up in it. And just look at all the funk that was collected on here. This is the engine-destroying trash that's hiding out inside a crankshaft that's already been cleaned 5 times prior, and you know all about that and have watched it all. I'm counting the rinse and oiling as a cleaning process. I'm showing this coming out during its 6th cleaning process. If you're not OCD, then you have to at least try to be for your final cleaning, and this right here is why.
Did you see that? I hope you saw that.
Not having OCD is not going to save you from the trash that's hiding out inside your used crankshaft's oil galley. I don't have OCD, I just play a guy on YouTube with it whenever I assemble an engine. It's called acting, but this is why. You've got to be really thorough with the used crankshaft. Whether you reuse your own or you buy one off of someone else, verify that this oil galley is completely clean, because it's just your main and rod bearings that are at stake. Foreign material's an engine killer, and 99% of the time it gets there because of the assembler. It's a hard lesson to learn, and I feel bad for every single one of those guys that it happens to, but nobody should be blaming their ultrasonic cleaner for this. The problem is that it's there to begin with, and it shouldn't be. It's very obvious how mine's helped me to do this here, because all I had to do was wash it all out with carb cleaner, but the stuff that I'm using is appropriately named. Follow all this up with an air hose to get it out while it's still wet to maximize its effectiveness. We're almost done. Next up is to clean up all the pin bore holes. Hit all 4 of those with an appropriately sized wire brush and then blast it all inside and out with compressed air again. You can direct where the air goes inside the crank by playing the crank flute and blocking other oil holes with your fingertips. Get them all, but next I'm going to try something I thought of in the last video just to check my work. I'm doing the same thing as I did with the fishing lure main oil galley cleaner thing, but I'm going to yank some white yarn through the crank, floss with it, and see if I can get anything on it to show up. I'm doing it for 2 reasons. One is to test its viability as a cleaning method. Of course, it won't get the dead spots. And 2 is to visibly check my work and see if, any of what I just did and told you was really accurate. I can show you this on camera. I can't find anything on the yarn even when I wet it with the carb cleaner. I'm just flossing until it starts shredding. The carb cleaner and the wire brushes are the stage where you can get this galley fully cleaned out if you're meticulous and you get it from both sides. That's what I learned from this, and we don't need to do any more of that. And now that we're completely done with the inside, I get to go back over it all one more time on the outside and get off what we washed out of it. My take on the yarn, it's the wrong material to clean anything with. You stand to leave more material behind compared to what you could ever remove. All I did was verify that my previous methods were more than effective enough to do this job, and there's no need to drill out the plugs because the dead spots are all fully accessible. Between the ultrasonic cleaner, busting all that stuff up, and the carb cleaner bath, that's all it takes, but be thorough. And now that she's ready to go, the block is too. Let's make way for this thing, and I want to check to see that I didn't disturb any of those oil clearances with my block cleaning methods, because the bearings all came out of it and got reinstalled. If I did anything wrong, then this test would be the thing that reveals it. Don't leave the oil holes facing straight up on the crank. That's not going to help with this one. Turn it a little bit first. I'm adding Plastigauge to all 5 of the main journals and getting this one ready for its torque sequence. Dry assembly on the Gallant. Never thought I'd ever be doing this one first, but you probably noticed that I've left all my precision tools behind on this job so far. All the work that I've done with that stuff has always been in an effort to determine their viability, and I'm far past that stage at this point. Yeah, I suppose I already made all the most technical assembly videos by failing repeatedly, or by rebuilding a blown-up engine using all but one of its previously out-of-spec internals. That should never have happened, but I made it work. What are service limits anyway? This has been in and out of my hands through 3 stages of quality control now. I'm giving it its 4th. Plastigauge is all this takes at this stage, and I'm blasting through this pre-assembly because it's less fancy than the final torque sequence. You don't have to have a rear main seal housing or to set the thrust bearing for it first. 3-stage torque sequence complete. Now just take it all back apart again, being really careful not to turn that crank. It's not the end of the world if you do it with the mains loose, but it can certainly destroy all of your efforts with the Plastigauge if they're tight. If that happens, you'll find yourself cleaning it all off and doing this job over again. That was almost me here. I bumped it while it was loose. Broke a little chunk off, 2 of them, but it's okay. It still left really clear prints on both parts for us to all look at. No problem here. It's exactly 2/1000ths, just like its neighbor, number 2, 2/1000ths. And the thrust main right here, we're actually just a teeny tad tighter than 2. I'm going to call that one 19/10ths. And now the broken Plastigauge ones. Number 4, we've got exactly 2/1000ths. Number 5, exactly 2/1000ths. Absolutely nobody with a 4G63 could ever complain about any of that. This is absolutely perfect, and if there's one main journal I'd ever want to be a 10,000th of an inch tighter than all the others, it would always be the center main. I'm the happiest Jaffro that ever happied. I can't improve on perfection, so I'm cleaning this thing off and it's going right back in the block. You probably heard me say something about a rear main seal housing. Yeah, I should have done this back in the previous video because it's part of 11.130. But here it is, going right on to 11.210 right now, and I need it. You saw how meticulous I've been with everything else. Now watch this one. 2 little dribbles of 2 + 2 on a coffee filter, a couple of those things, and a razor blade, and now she's, wipe it off, blow it off, it's good as new. I have to press a new seal in it. That's the part number right there, and I've got both of the specialty tools for its assembly. The 1G units take 2 specialty tools. MD998376 is the seal installer tool. It's got a relief that holds onto the seal, and it protrudes through the seal to the depth necessary for you to not crush the seal or the housing while you're driving it in, beating on it with a hammer. It's convenient, but if you're creative, you can do fine without it. The other one is MD998776, and all it does is press in the oil seal retainer ring, and you probably shouldn't put that one on backwards like I'm doing right where it's upside down. The oil hole's supposed to go against the flat side. Somehow I got disoriented which way it goes because the block is upside down right now, and don't worry, I'll fix it. I have to. It's much easier to clear the engine stand with this thing if you hang it on the crankshaft prior to trying to install the crank into the block. But I'm still not done with it yet. There's also a gasket and some RTV that I gotta spread around on here first. I put the thinnest of thin coats of RTV, smeared all around the rear housing where the gasket lines up. Its job is just to stick the gasket in place while I install this thing on the crank and get it all in place. Manual says to do it, but I got to get my butt moving because I need to lube and torque all of this before that RTV fully sets. Now just imagine me lubricating the main bearings while the camera battery dies. I am not particularly proud of myself at this moment. I've already done this once before. You notice the crankshaft is already in it and the caps are on. I've already lubricated the bearings, and I realized that I missed a very important scene. I want to be able to show you exactly what my mains torque sequence process looks like, so I had to go back and take it apart, and we're going to reshoot it. Like I said, not real proud of myself, so I can't redo those previous scenes of me installing a crankshaft into a pristine clean set of bearings without redoing the previous 2 videos worth of work in order to be convincing. So I'm just going to admit my mistake, and you guys know what lubricating bearings looks like. If not, this isn't the last engine I have to build, but I'm just using a main stud to spread the ARP Moly lube with because it does a really good job with the same thread pitch. And first, before I go too far, I just want to make sure that all the main studs are still snug. And you just do this finger tight. I just want to make sure they're all the way down. You don't have to put any torque on these. Good, none of them came loose from me taking the mains loose. Alright, the first process that I wanted to show you is setting the thrust main. And the reason why is because this bearing is a 2-piece spherical bearing. It goes all the way around the joint, or it's hemispherical because it's 2 halves. Those have like a saddle-like fit where it straddles both sides of the mains for a thrust clearance. And on the mains thrust journal, what you would want to be looking out for here is to, because it's 2 separate pieces, is to ensure that both pieces are lined up perfectly straight. The easiest way to do that is to put a load on it with a flat surface, like the crankshaft's thrust journal. And you would do this by putting a little bit of pressure on the crank, pushing it towards the front of the block. And then once you have that pressure on it, give her a little whack. Maintain that pressure. You don't have to pull real hard or anything, but while you're doing that, snug the thrust main. Might as well go ahead and do the rest of them. And you see I'm following the torque sequence here. There you have it. So with the thrust main set, it's time to torque the main studs. These get 60 foot-pounds with ARP moly lube, and I'm going to follow the torque sequence just as we did, snugging them all down. You see the torque wrenches on 60 foot-pounds. Like I said, I've already done this once. You do this in 3 stages, 20, 40, 60. Clicker style wrenches and digital torque wrenches can actually yield different results if the operator has never been conscious of how differently they function and they try to use one just like it's the other. Digital jam uses a strain gauge and the clicker uses a mechanical breakaway. In either case, you still have to move slowly, continuously, and consistently to hit your target, but the clicker tends to make the operator briefly exceed the torque load once it reports. This isn't necessarily bad. The bolt will stretch and settle in the right spot if they're not being jerky with the wrench. The digital wrench will false positive though if there's any jerkiness near load, or even sometimes the slightest little muscle spasm in the operator. Next up we go to 40 pounds. At this point they need to hold it at that torque load until the bolt settles and stops turning. The clicker style wrenches will actually prevent this more than the digital ones will, but the feedback provided by the digital wrench will actually provide the operator with more precision if they use it right. I just want you guys to be conscious about stuff like this because even tension across the bolts is what you're going for here. Now we do 60 pounds. This isn't a race just to get it done. You can achieve a great deal of precision using either kind of wrench. You just have to be slow and consistent with your torque method and do the exact same thing on every bolt throughout the sequence, and you'll be successful. Always use the lube that your specs request for the torque load and give the lube and the fasteners all the time they want to stretch and settle as you approach it. And there you have it. Now if you did everything right, you should be able to turn the crankshaft with 2 fingers. There you go. 2 fingers. Y'all didn't need to see me lube the bearings again. It's looking good. I'm loving it. Some really sticky stuff. I used Royal Purple Max stuff. It's the same as the red Permatex stuff in its viscosity. It's real sticky. It stays put on the bearings. That's why I like it. And I like the Permatex stuff too. So not picking favorites here. It's just what I have. Next up, we got the thrust clearance measurement. This one's really simple. You can use feeler gauges to do this like the service manual says to, but why not just use a dial gauge? It's so much easier for me to film and focus on. It kind of gives us a little bit more info, and you press the crank all the way to one side and you zero it, then press it the other way, and what do you got? I just did a backflip. Did you see it? I think I might have been out of the shot though. Dang it. Oh, no. Probably shouldn't do that again. Not at my age. That's smack in the middle of spec for crank end play and a great place to start. That's going to make for a great oil film layer everywhere. Not too tight, not too loose. To me, that's exactly where you want to be. 4.5 thousandths. Yeah, I know I wrote 43 tenths up there. I'll fix that. It looked like it from where I was standing, but the camera doesn't lie. We need some balance shaft bearings up in this bleock. I ordered a bunch more stuff to round out the blanks for the other 2 builds, as well as this one, because I robbed a few parts from it, and I really shouldn't do that. The bearings that I'm cutting open came from that order, and I also have the OEM balance shaft bearing installer tool that's designed to install any one of the balance shaft bearings in the perfect position. This got here just in time to keep things from getting out of hand. I didn't rob anything else. I got enough heat barrier gaskets for everything. Ison 2G water pump, and that's significant because I also have the Ison 6-bolt water pump, as well as 2 factory OEM new in-box 6-bolt water pumps that we'll take a look at later. I got 2 sets of ACL balance shaft bearings for doing balance shaft deletes. I got a few bolt kits, valve cover, front case fasteners, water pump, Anywhere I came up short, replenished what I stole, and this kept me from wasting a really expensive set of factory balance shaft bearings on something that's not going to have balance shafts in it. That's totally unnecessary. I don't need to use OEM bearings for this one, not this time. The ACLs are a fraction of the price, and they're going to serve as a plug anyway. You know, back to that tool though. With two bearing receivers, you'd think that you can drive them both in the same time. And you can, as some people have unfortunately learned, but don't ever do that to yourself. The end of this tool unscrews, and that's for a reason. You can get it stuck in there if you do that. Even though the end of this tool unscrews, the outer bearing, or the closest one to the handle of this tool, is only 1 millimeter larger than the inner bearing. But it's several millimeters thick, so if you do them both simultaneously, then you can't get the front part of the driver back out of the block. Furthermore, there's nowhere inside the block's casting where you can unscrew it and sneak it out. So you'd have to remove the outer bearing after driving it in just to get the tool back out. Do them one at a time and start with the inner bearing, unscrew the end of this thing, and then do the outer bearing. That's the trick. There are universal bearing drivers available, but this one is the factory MD998373 driver. There are 3 different part numbers for the balance shaft bearings, and here they all are. The one marked solid is the only bearing on the oil pump shaft, which is the rear shaft if you're standing in front of the car. There's no oil hole in that one. That's because the journal is oiled by the oil pump shaft itself. The one marked solid goes in the journal right there. The rear bearing on the front shaft, if you're standing in front of the car, does have an oil hole in it. Both of them do, actually. The rear bearing for the front shaft shares the exact same physical dimensions as the one that's marked solid. It just has a hole in it. The front balance shaft bearing is also a Holy bearing that's different from all of everything else. I really only need the front shaft bearings for this, but I'm going to use the cheap ACL bearings. But all 3 of the ACL bearings happen to have oil holes in them, even for the one that doesn't. They don't care. If you're using balance shafts, you have to be very careful to align the oil holes of the bearings with the oil holes that are provided in the block to lubricate the shafts. One way you can do that is to mark the position of the oil hole on the block with a marker so you can see it looking through the hole, and also on the edge of the bearing so that you can align your marks as you drive it in. But if you're running balance shafts, then you need to actually align the oil hole on the opposite side of the block from where the oil hole is to block off that oil supply. You're basically using the bearing to plug the main oil galley, because that's where these balance shaft galleys are all tapped into. Here we go, front outer. Since I'm not running balance shafts in this block, I rotated that hole well out of the way before driving it in there. Don't put the thing back on the end of this tool that you just watched me unscrew, and only drive in one bearing at a time. You've all been warned. I've never done it, but I know somebody who drove in both at once, and he'd want me to warn all of you about that. Yeah, he never deserved that. It's punishment. That right there is where this tool sets the bearing. The driver has an inner lip that's slightly smaller than the OD of the bearing so that it sets that depth. Just be careful when you're doing the inner bearing. At the end of the tool is screwed all the way down tight. If you read ahead on the whiteboard, you'd know you're about to meet the Gallant's pistons. These are Wiseco HD, 8.5 to 1, 10 overbore, or 85.25 millimeter, whichever you prefer. Essentially, these are the 2G pistons, but all of you who have these pistons know yours don't look anything like these do. That's because even though they came out of the box factory dry film coated with anti-friction stuff, the dome is also ceramic coated, and there's an additional anti-friction tough skirt coating applied to the entire bottom half of it. The ring grooves remain polished to maintain optimal thermal and oiling functions, making these an aftermarket forged upgrade plus for a 6-bolt DSM. I bought BC 6-bolt H-beam rods with the bigger 2G pin bores and upgraded the wrist pins, and absolutely all of this is total overkill for anything that I'll ever need on the street. But it's higher compression, higher efficiency, and a crispy clean burning engine here and forever forward for number 1229. So what I'm doing right here, I'm weighing the pistons, circlips, and the entire ring pack together to determine their combined weights. It became immediately apparent that the rings have already been gapped for me and that all of this has been done previously by somebody else. I just need to check the compression ring gaps to determine their order and put this stuff together and send it. It doesn't matter if they're installed in the piston or not, you just weigh it all together and write it all down. I'm doing this without the pins because in my experience I've always had 1/10 of a gram or so variation in the set to play with, and the pins aren't marked, so that might offer me some creative freedom. You'll see me weigh everything several times. I'm running on a set of no-name batteries that have been consistently half full for the past 6 years since I bought the scale. It loses its calibration every now and then, but you can tell. Hit the tear button and it fixes it, clears it right up. You can see the calibration weight in the double bag behind the post on the rod balancer. I checked it, it's dead on 500 grams, so I figured I'd just roll with the batteries that won't die. Here's the pins, beefy ones. bigger, fatter ones made of better stuff than any of the 6-bolt blocks ever came with. It became apparent that the battery voltage starts strong and then fades after a couple minutes of use, or like 10 to 20 measurements. It started shedding a couple of tenths of calibration. I know that I've been making videos long enough to be better prepared for this example. I could get some new batteries, but once again, the tare button cleared it right up for the next 10 or 20 measurements until it does it again. Would you look at that? I get none. No creative freedom to play with here whatsoever. They all weigh exactly the same. Okay, let's move on to the rods then, shall we? I need to get a lot of different weights here. And look, the bearings are pre-installed. Coming in at a tad under 623 grams for number 1. Write that down. Rods are large, so you have to place their center of gravity in the center of the scale and always take your measurements in the same spot with every rod. Look at that, 623 grams. We're looking good so far. How about number 3? Another one at exactly 623. We got a pair with just 3 cards dealt. The suspense is killing me. Let's draw number 4. And no, not the scale. Come on, scale. Work with me. Tare button. There. Oh, yeah. Uh-huh. 2 pair. Jaffro's all in. This looks like a great hand to start with, all within 0.2 of a gram. Let's break down the big ends and the pin bores now. I always wanted to make a rod balancing video, not just because I wanted to use this fancy Proform 66844 rod balancing jig that sells for about $350 if you include the cost of the scale and the test weight, but to make up for what I did with that balancing job on the Hyundai. I only addressed its linear or its reciprocal balance, but in addition to the reciprocal balance, there's also the rotational balance, and where all that weight is located on your rods is going to determine how those linear and rotational forces affect your crankshaft. It needs to be throwing around some very evenly matched weight in its rotational balance as well as the reciprocal weight that it's pushing and pulling. So all of the weights of the components matter, and they matter as an assembly. What I'm doing here is weighing the big ends and the small ends of the rods and writing them all down. They're assembled with bearings right now, and the trick with this rod balancer is to ensure that the hanging arm from the balancer remains 0 degrees vertical while you're centered on both pieces of the jigs, and the rod's hanging level between the jigs on top of the scale. Any angle on that rod or the dangling arm from 0 is going to begin to affect its balance. Once you get it hanging right and you repeat consistent measurements, all you need to do is write them down either on the rod or on your blueprint somewhere else. I'm just using my whiteboard. It helps all of us here. After you have all your numbers from the total weight, the big end and the small end weights, and in a way that helps you reference each rod, most people who balance their parts would just match the specifications of the lightest one by selectively removing material from wherever it's needed across the set of rods. But that's only if the weight can't be achieved by just shuffling around other parts first. You know exactly how much all of this weighs now. Most manufacturers shoot for less than 3 grams of imbalance in their rotating assemblies. These are for stock engines. Race engines, of course, would be more precision. But Mitsubishi stuff from the factory usually stays under 2 unless it's installed in someone's Elantra. Then no, the rules don't even apply. What I've got right here are rods within 0.2 of 1 gram. Big ends within 0.3 of 1 gram, and small ends at 0.4 of a gram. So I guess I still don't get to make that rod balancing video for you guys after all. I'm sorry. What you see if the manufacturing target is 3 grams, what you're looking at here, these numbers are 10 times closer to perfect than that. This work's already done. When you're looking at these numbers, imagine the center main, the number 3 main, splitting those numbers in half. You got the right side and the left side of the crankshaft. The weights on either side of the thrust main, in other words, the halfway point, are 1/10 of a gram apart only on the big ends. And you'd split that difference because we're talking about halfsies here from one to the other. It's only, it's going to balance out like that. The small ends and the overall weight are still exactly the same. We know the pins are the same, and that means the only variation that I have is the pistons. I may remeasure those again once they're assembled to see if my scale got the best of me, because I discovered its little battery problem after I weighed the piston and the ring packs. Might have got me. Now, I know that previous example isn't at all what you're trying to go for here when you're balancing a set of rods. I was just interested in how that actually lined up so evenly across at only a 1/10 of a gram difference from one side to the other. That was cool. What you're really trying to focus on is the weight that's traveling together, which would be the numbers 1 and 4 and the numbers 2 and 3. And if you look over here, you notice that there's a 0.4 gram imbalance in the rotating assembly. Well, I went back and checked all the numbers, trying to see if the piston weight got me on the scale or not. And no, it turns out they're actually correct. That's exactly what I measured was what they are. And then all this wound up making sense to me really quickly. If you were to take number 1 and 4 and you add them together, and you were to take 2 and 3 and add them together, what you come up with is 735.8 and 736.3. Now if you were to take the weights of the pistons and you add it to the rods, and you see that 0.4 gram imbalance there, the heavy set of pistons winds up having 0.4 grams lighter of rods. You end up with this one right here wouldn't change at all, because that's its mean. So hey, we're within plus 0.1 gram of balance on the reciprocating mass, 0.2 grams on the rotating balance. This is going to be the smoothest running 4G63 I've ever owned. Maybe some other time you'll see me grinding a rod, but not today. As far as these are concerned, I can't improve upon this. I could turn this into a big waste of time, a big waste of money, or both if I tried. Of course, balancing anything other than a flat plane crankshaft is going to be more involved than anything that I showed you here. But I'm ecstatic that this is the example that I get to show you, and that this is what's going into my sleepy, gallant grocery getter. Let's go ahead and finish this rotating assembly. Sometimes you really have to fight with these circlips, but it's not the circlips' fault. Really, it's always just been you all along, because they don't care. They don't even know you're there. The more you do it wrong, the longer it takes. Start one leg of the clip in the opposite side of the gap drilled into the side of the bore. I'm using a nylon spudger that's not going to scratch any finish on this piston if I slip, so I can compress the clip while pressing it at a point beyond the bore gap with my thumb. Do not pry off that little dimple, because you can kink or damage the clips. Do your work past that little dimple, but compress it and squish the other side into the hole and seat it. Make sure it's snapped in all the way around, and compress it with something just to make sure. That little dimple thing there, yeah, don't dangle your ends out of that gap. It's not there for easy removal of the clips. But that is a bonus once you make it all explode and you have to take it apart later. It's time to stab these pistons and rods together with some wrist pins. I turned this one upright the way it sits in the engine bay to keep this example familiar, and I had to flip the order of the rod assemblies on the bench because the block is 4, 3, 2, 1 against it, and I had them in 1, 2, 3, 4. Rods, caps, and pistons are all directional. Get any single one of those wrong and it's an automatic F. The tangs go on the same side of the connecting rod together, and you can see right there on the other side the flat edges butt up against each other. Tang to tang, flat to flat. On a 1990 to 1999 4G63, the tangs face the exhaust side of the block. How do I know that? The only place where the rod orientation is documented in the Mitsubishi service manuals, wherever the 6-bolt is concerned, is only in one single illustration. I read the whole rod section in all of them and it never mentions it. The only way you'll ever find it is to zoom in and look at the pixels. You can see the tangs on the bearings in the illustration. It's literally only a few pixels. You see right there, it's all in the drawing. I can also confirm that the Evo guys' engines are backwards from this. Not only this, your heads flow the wrong direction. So for Evo owners, the tangs go on the intake side. The rods are still oriented correctly in the block the same way as they are for mine. It's the side of the engine that does the intake and exhaust business that's flipped. And yeah, you guys are the backwards wrong ones. DSMs are here first. Putting the last circlip in once the wrist pin is installed is a completely different experience.
Easy.
Since you lose a little bit of your wiggle room, you just have to become a little bit mightier. You can always tell when someone uses a screwdriver to do this because the bosses always get scratched. The spudger's not even affecting this coating. You know that you have the direction of everything correct when you're installing all your rods with the tangs facing the exhaust in your 4G63, and then all the pistons directions indicators all face toward the timing side of the block. Whether you're installing the pistons onto the rods or the rods into the block, always do the direction based off of the orientation of which way the tangs are supposed to face. Don't install your rod assemblies based off the mark on the dome of the piston. If you're always certain that you did both processes based solely off of the tangs, then the piston domes will always reveal whether or not you did the rest correctly. You did it like this because basing the rod orientation off the piston marking will hide a mistake rather than reveal it. That's how you accidentally install a rod backwards, you know what I'm saying? The main thing is to base all of it off the tang orientation. After a week-long soak in ATF, it removed more stuff. I was pretty proud of that. That did its job with the seasoning, but I'm stripping it and re-seasoning it again because it's assembly time. And part of this assembly is dry. I want to get to know my parts and make sure that I didn't screw anything up in handling, so I'm going to do the plastic gauge test to check the rods. Make sure I know what my parts want from me. Because these are about to meet the block for the first time and first impressions are important, I'm giving them a final cleaning job. That's the whole white coffee filter and denatured alcohol thing with a meticulous inspection. And of course it paid off. Nice little chunk of metal shaving right there from the manufacturing. Cleaned everything up, rods, pistons, ring grooves, the bearings. You can skip the pins, those are lubed already, but get everything else. Next, get the rings in the right orientation, find their marks and place them all face up. The oil ring doesn't matter, but the compression rings do. Some are marked, some are stamped, sometimes there's a dimple, sometimes there's an included chart that illustrates a cross-section shape of the ring. But these are etched with their sizes on the top side already filed. The flat black one sure is a whole lot easier to read. All the compression rings go marked side up when you install them. There's science behind all this, but for the sake of time, I'd like to just believe the combustion chamber's arrogant and wants to see itself in the shiny mirrored ones, so those go on top. Don't need them for a plastic gauge test, but if I pass, they're next. Now to separate the caps and clean up the parting lines. This is just a test, but you still treat this like it's your final assembly. And now when I orient the rod with the tangs facing toward the exhaust side, look at that. The mark on the piston is facing the timing side. See? There's the tang, exhaust side, flat edge, intake side. The mark on the piston means that I started putting this assembly together right. Go by the tangs. Let the mark be your answer, not your guide. There's a darn good reason too, but first I need to cut up some plastic gauge for this. I'm using the red again because it does between 2 and 4 thousandths, and the spec for these particular rods are between 2 and 3 thousandths, so that's nice and in range. Now with the cap separated in a completely different place from the rod, you know to put the cap towards the exhaust side, so if you install this cap facing that direction, you don't even need to see what you're doing to know that you did it right. And that's convenient because doing this with a deck facing up, but for a good reason of course, there's no rings in the pistons and they'd fall right out right now, but I can do this without looking and get it right. But don't completely remove the bolts yet. Use your socket on a bolt head and smack it to separate the rod cap and then take both bolts with the cap the rest of the way out. And there you have it. It's smaller than the 2 mark and a tad bigger than the 3. So that puts me at about 2.5 thousandths here. Spec between 2 and 3, so we're off to a great start. We'll do all the rest of these first and then we're going to look at them, but I'm grabbing the next one and just going to move down the line. Alternate snugging both sides hand tight first. I'm doing a 2-stage torque sequence. I'm just splitting my goal of 45 pounds in half. And once it's torqued, just break it all right back down again. Whether you're doing your final assembly or just a plastic gauge test, avoid scraping or banging any of these parts into one another on their ways in and out. Put your hand below them to catch the rod before the piston's fully inserted. Carefully guide it over the crank. You have bearing surfaces and journals exposed to sharp edges here, so just be careful. Don't go flipping the stand over either, because gravity. All that will change later once we put the rings on them, and to tell you the truth, I'm really getting excited about this one. I can't wait. It's past my bedtime, but I really don't care. I'm going to get this done. It doesn't really become apparent that this one's wider than 3 thou in this shot until I mash the plastic gauge close tight to it. Plastic gauge lies whenever there's a shadow under it. It's right there between 2 and 3 thousandths, which is exactly spec. That's where I want to see it and what it's supposed to be. So, yeah, it's only a plastic gauge test. You're only going to get a pass or fail. Number 2 is coming in at looks like 2 thousandths, a tad over most everywhere else. It's not quite the full red mark, so it's a little smaller. It's a smashed piece of plastic after all. I'm going to give that one a 2.2-ish. Don't ask me why I did number 4 first. Hard to read it, except that no, it's not. And remember what I said about the shadows. The plastic gauge is not there, but its mark still is. It's just a thing that it likes to do, and I'm grateful for it. It's bigger than the 3 mark here, but clearly smaller than the 2. We're right there in the middle of spec again. I'm giving that one 2.5. Number 3 looks fantastic, just like the others, right between 2 and 3 thousandths. And a bit on the lower side, really. I'd have to say with my sloppy plastic gauge test that all of them probably ring in around at 2 1/4 to 2.5 thousandths, which is perfect for the beginning of life with these kinds of rods and how this engine is going to be used. For final assembly, everything gets stripped off. It's another final cleaning cycle, and it has to happen, but this time I have to clean off all the fasteners as well. The grease gets displaced under load, and it also degrades in quality a little bit with each torque cycle, so I felt like that got the best of me with my plastic gauge test. So I bet all 4 of those rods are dead on 2.2 really, but I'll spare you why I believe that because I passed. Of course I have to clean up the rings too, starting with number 1. Might as well, nothing stopping us. But let's talk about those rings for a second. The oil ring is stamped with an extra ridge right around the inside of the top and bottom. You can just barely see it there. That's to catch the oil wiper rings, and that also locks this ring in place. So the ends of this one you see here are symmetrical and they do not overlap. It's bad if that happens. This needs to float freely around in the groove, just like all of them should, just a little, and any overlap anywhere will bind in the grooves, and you don't want that. Side rails or the oil wipers are out of phase 90 degrees from the oil ring gap, but they're fairly flexible. Definitely the second and third most cooperative rings of all 5 of them in the set, but the easiest way to install the oil rings is to slap it on top of the piston and sneak one leg around to fill up the gap above or below that oil ring. Use ring pliers for the compression rings because they're extremely brittle. They spread the load over an entire ring instead of just where you're grabbing it from with something else, giving you much more control installing them even though they can be a little bit finicky. They're intended to prevent excessive stretching of the ring because though they snap easily, they can also bend and warp out of shape while you're installing them. I'm going to speed through the other 2 assemblies and then we'll take a close-up look at the oil rings again. The oil ring goes on first without overlap and the rails lock it into place. Just look at that big beefy wrist pin right there, people. No chance that sucker's ever going to bend and crack the pin bosses of the piston. I like to put 22mm wrist pins in all my builds, do the lower and then the upper oil wipers, and then work your way on up the rings. Same with the compression rings. If you do those backwards, you just make things harder on yourself. And you might think that I skipped a step. I didn't file the rings because somebody else already did. I absolutely did check them, and I ensured that the one with the narrow gap went on top the way they're supposed to be, the way they were marked for me too. I'm so happy that I haven't had to modify any single thing at all since this started. Everything I've measured and put together except that rear main seal cover went right the first time. Everything fit. There's not one single time in my life that this has ever happened to me. All of this was so far out of my budget on this car, and an impossibility without all of you watching and supporting me on Patreon. I really needed this, and I know all you did too, so I think it's worth every single penny for this experience and example right here. Although for the cost of all the tooling that you've seen me use all along this way, all of that far exceeds the cost of paying your machinist for the final cleaning and assembly, especially if they're this good at the machining part of things already. Good gravy. But I know that's not what all you guys are coming here to see, so that's why I did this. Once this oil ring is locked in, it's tricky to turn any single one of them without the others. You can rotate all your rings into place after you install them, but it's much easier to fine-tune them into place if you install them as close as you can. I wrote the diagram on the whiteboard in front of me. You've probably seen it several times by now, and that's my reminder for which way the rings go. These rings have many opportunities between now and when they go into the block to be disturbed. I promise to disturb them constantly until the block is satisfied. This is one of the greatest combinations of tools that I think I've ever combined together. I used to hate this stretch gauge thing because I gave away my nicest dial gauge that could have worked with it, but it didn't work very well anyway. A 2-inch drop gauge is the game changer for this job. These bolts were made to be measured like this. They're cut to self-center, and that's why you see me spinning them just to make sure. I'm writing it all up there on the whiteboard, doing this once again, so you'll figure out why I stressed this point multiple times earlier. Document these lengths based on where the tangs are on each individual rod. They're all different lengths, and once they're torqued, they're going to become completely different lengths again. And they're designed to do that so that you can check them. So I have to measure each one, and I have to install them according to my own documentation because I need to come back here again and reference it later for the end result. The rod caps made a great placeholder after the bolts were measured, and now this is their reward. It's their big day. I'm just going to go ahead and prep these with the assembly lube included with the rods. I just cleaned off my spudger real good and used it to spread on the threads and under the bolt heads. Skip ahead, man. You're lubing bolts. I didn't bother cleaning all the lube out of the inside of the rods. They've never been contaminated, and a little extra lube isn't such a bad thing there. But I wanted it pressed into these surfaces real good so that it spreads right where it's needed when it's needed. Time to clean that spudger again, though, because I forgot to clean the other half of my plastic gauge test up from earlier. Bear with me a moment. Darn. This one gets the denatured alcohol re-prep, and I just reset it and did the re-cleaning just like everything else got. And I want you to know that I spared you from all of this with the rods and pistons because that scene was absolutely brutal on the ears. But this one right here, this time I'm going to let you have it. And of course, now all that that's clean and lubed, the best way to not contaminate it is to change gloves. Gloves are your friend. New gloves save time and effort. You can double and triple up latex gloves to still have some sense of tactile feel and convenient quick peel cleanliness, but I'm fresh out of those. course, I got to clean up the tools that I have to use on those parts too. Clean everything that's going to touch these parts or your hands. Clean up the oil can. Clean the tip of your lube bottle, your sockets. I actually went a step further and cleaned all the moly lube off the outside of the mains, because what's doing something important right there is already inside of it on the threads under the nut and the washer. It doesn't need to rub off on your gloves and everything else while you touch it. Time to put some fresh ATF back on these bores because it's party time. This is the last step before I make this rotating assembly one big happy family. ATF doesn't glaze the cylinder bores on first startup, and it helps to seat your rings faster. That's why I use it here. And at this point, you'd think that I immediately contaminated my new clean gloves, except that everything I need to touch going forward is supposed to get ATF all over it so it all checks out. Since this piston's next stop is the ring compressor, first it needs to be lubed. The rings uncompressed are currently bigger than the grooves, so they're going to roll around and move while you rotate it to get it all. ATF is still my fluid of choice here. Fill the whole oil ring, soak them. The rest will be fine. It's got an anti-friction coating on these pistons, plus the bores are lubed. The compressor's clean, and what you put on the piston will squish all around it before it goes in the bore. So when you're clamping your piston up in that ring compressor, first check to make sure all of your rings are located correctly in their grooves. There's that diagram that I was talking about. Depending on what you're building and whose pistons you're using, it could be different, but these factory locations that I wrote up here on the board are the same ones that my pistons are supposed to have. So that's what I'm going with. Well, when you're clamping your piston up in the ring compressor, first make sure that you got all your rings in the right orientation, and then try to keep your eyeball between the compressor and the edge of the piston to watch those ring gaps and make sure that they don't move while you're clamping it down tight. And once you clamp it all the way down tight, make sure it won't even click again. That's when you got it right. I added a little ATF to the compressor around the crown, lubed up the rod bearing, checked my tangs, and carefully placed the assembly on the block. You should have a little bit of the skirt sticking out. The bands on the compressor go all the way around the rings, but that skirt serves as a guide for your center. Press the tool flat and square against the bore with a wooden hammer handle. The compressor has a lip that holds onto the bore. I give it a gentle little analytical taps, concentrating on any feedback or movement from this style of ring compressor. Anything occurs, do not tap. Stop immediately. But like you saw, I usually have really good luck with these. I went ahead and did number 4 out of frame, so we'll skip that, but I'm going to flip this over, and I did press the piston down a little bit in the bore to help the rings hold it in place. Now I just have to lube and install the caps on these and torque them. You know I accelerate my videos to save you time. We're going to do this in 1 minute instead of 15. Spend no less than 25 seconds on each bolt tightening cycle. Whether your wrench goes click or it's a digital wrench with feedback, you want to gradually and slowly increase your torque load about a pound at a time. Just creep up on it. You can't see what you're doing with a clicker style wrench because it doesn't give you any feedback, but if you hold the digital torque wrench at its torque load, you'll see that the handle of the wrench still continues to turn slightly at that same load. Or the torque drops if you hold it still. Between the lube being displaced and the stud material stretching, the wrench continues moving at that torque load. So you're trying to install that tension into the bolt, and it's trying to stretch while it's under load and turning further. That stretch is what makes your rod caps actually stay put. It counters the load that are experienced by the crankshaft and the rods together spinning at high RPMs. And we're halfway done. Moving on, number 3 and number 2, starting with number 3. Give her a splash of lube, clock the rings, clamp it down, put it in the block, square it up, center the piston, drive it home, and check it.
Stop. Come on over there.
That's what I meant by gentle analytical taps. All it takes is one tap, and after a ring pops out, to kink, bend, or otherwise permanently destroy itself. And I immediately put my brakes on right when I felt it pop. I still had to fight with it a good bit because the top compression ring was already halfway in when it happened. After a good inspection of the edges, I reset and finished what I started. It was fine. Number 2 got the exact same treatment, except that I did it right the first time, and I flipped it all over to install the caps and torque the last 4 bolts. Tangs, same side, same torque sequence as the other ones. Number 3 thought it was going to get me. Had to say nay now, my damies. Nair nada. Same torque sequence again. I split it in half, and we're going to talk about that right now because ARP 2000 bolts actually say not to do it that way. I did. Sorry. They say to hit 10 pounds on all of them first, and then complete your final torque load in one movement from there. You should base your torque load off the bolt stretch rather than what some sheet of paper says to torque it to, but I picked 47 pounds because it's right in the middle of what some piece of paper says to torque it to for my bolts. I had other reasons too, and I gave them to you already, but there it is right there. I'm using the 3/8" jammies. If only there was some way to highlight that better for you. You saw me measure and document the bolt's lengths. Now we measure their installed lengths. Make sure it's still zeroed and the gauge fits up in here real nice. You get that nice little finger loop thing that lets you balance it easily while you center the point on the bolt and then lift up and find the center of the bolt head, which is the lowest measurement that you can achieve on the gauge, and write that down right above each one of your documented free lengths for the corresponding bolts. Yes, just like that, only neater and more organized, yeah. Now subtract them. What do you all get? Hey, spec is 5 to 6 thousandths, and I don't see any sevens. Honestly, it's only a thousandth graduated dial gauge. My tenths are guesses based on where it landed on the marks. Despite that, I don't think that I could have ever hit the bolt stretch spec any closer on my first try. Could I improve on that? Yeah, I could buy a 2-inch drop gauge that measures in tenths. Probably get better math. Might be even closer with that. But thousandths is enough, though. Really. You just know that if you round that thousandth too far of what you see on the gauge, then you could cost yourself a thousandth in the math, and that's why I guess the tenths. That's why I try to avoid that. Smooth torque sequence is the key to getting even bolt stretch, though. Now I guess I can put these oil squirters in here, and I'm going to start doing that with the crush washers. I got 8 of these things right here. One goes on the top and one goes on the bottom of each one of the check valves, and the squirters sort of work like banjo bolts in between. It can be a juggling act to get them all in place, and it's even tighter fit with the crankshaft in it, but long flat nose pliers are the only trick you're going to need out of that whole bag. You can set the washers, the squirters, and the check valves all in place with them. You'll need to rotate the crankshaft around here and there to get clearance for your sockets. And after you run all these things down by hand tight, and seated the pins into the block fully, grab your torque wrench and a 17mm socket, set it for 24 foot-pounds, and slowly squish them all down tight into those crush washers. These were a part of section 11-130, just like the balance shaft bearings and the rear main seal cover were. This video rounds out the entire section with just a dipstick. Rings, piston, pins, rods, bearings, and a crankshaft were the bulk of section 11-210. The only thing missing is a flywheel, a damper pulley, and some bolts, which we'll get to once it's swinging from a chain. But for now, I have to fix my little screw-up, which I caught thanks to the magic of video editing. It's such a good thing that I remembered to dangle this rear main seal cover onto the crankshaft when I installed it, so that once it was installed, it could not be removed again while it's on the engine stand. That was such a great thing. I totally couldn't have just figured that out at any time later. But thanks to that, I got to lift an assembled block on and off of my workbench. That was fun. This rotating assembly is finished. All those parts got cleaned that I showed at the end of the last video, just like I promised, and while I'm rolling out, I want to explain my gratitude, not just for all of you following along, but especially for those of you who have contributed to my success over the years in bringing everyone this example today. These documentary-style productions are not inexpensive or algorithm-friendly, but for all of you who comment, "Don't change," it's because of these names that I've consistently stayed the same while managing to find new ways to still make improvements. The ends of my videos are typically adorned with the names of everyone who's actively sponsored that particular video's production, along with Rojo del Chocolate's accompaniment, but this time, this video's conclusion has honestly been years in the making. I know people's circumstances and priorities change, but so many people have contributed to making this victory possible for me that this time I owe it to all of you to say thank you. And that's a lot of names. The people who have sponsored my journey are why, when I hit snags in my builds, rather than settle for a fix, I raised all of my standards, expectations, and production value. While YouTube continued changing, they stuck with me, so I keep doing this, and I'm so grateful for all of this today. They're why I invested and, like I said, gambled on a better outcome. No regrets. I couldn't do all this like this without their help. Today, the work that I'm showcasing was performed by the best machinists in the industry, and it's a road that I never imagined traveling down when I set out to do this work. That's my reward and motivation for this. All of these people are why you don't see sponsored product promotions. This whole channel is solely fueled by your gratitude, so if the videos are better today, it's because of all of you, and I think that's incredible. I love you guys. There's room for all of you if you ever want to come back. So while I get set up here for the next episode, know that this work never stops and I love doing it. I'm always crunching and compiling the next one, looking for new ways to make it better. Thank you all for your past, present, and continued support. And until next time, stay tuned.